Thank you for listening today, and thanks to the meeting organizers for the opportunity to give this talk. So what I'm going to try to do here is give an overview of some of the more commonly used animal models in the headache research field. So just to start with, what are the goals and limitations of animal headache models? So in terms of the goals are to provide mechanistic insight into the pathology that contributes to headache disorders, identify novel targets for new therapies, incorporate one or more translationally relevant aspects of headache in humans and bring that back into the model. What are the limitations of animal models? Importantly, animal models cannot and will not fully recreate the entire experience of human headache or migraine. The endpoints that we use to test in animals will always have questions around their similarity and translatability to human headache, just simply due to the nature of us not being able to verbally communicate with animals like we can with humans. So there are a variety of ways to study headache in rodents. This is a nice image here from a review from a couple of years ago. And one could stimulate the meninges with mechanical stimulation, electrical stimulation, chemical stimulation. One could use a hemiskull prep where you could measure release of various things from the meninges. You could look at brain slices, you could do electrophysiology, you could look at histological markers. You could do in vitro electrophysiology, taking neurons, commonly the trigeminal ganglia, out of animals and culturing those in a dish and studying them in vitro. What I'm going to focus most on today is behavioral models, stimuli, a variety of different kinds of stimuli that are given to animals and a variety of different ways that headache is measured in these animals. So starting with the endpoints, what kinds of behavioral responses do you test in rodents to determine whether a headache is present? So we'll talk about tactile hypersensitivity or allodynia, exploratory or locomotor activity, avoiding light avoidance, and condition place preference and condition place avoidance. So starting off here is a rat in this case, placed on a mesh floor, and this would be inside of a chamber ideally. And one could use von Frey filaments on the paws or more commonly in the periorbital region to test cutaneous hypersensitivity or cutaneous allodynia in these animals. And the way that I'm going to organize these slides is I'm going to talk about the concept behind why this is used in animal models first. I'll tell you a pearl about the use of that model, and then I'll tell you a pitfall associated with the model. So the concept here is that von Frey thresholds are used to capture cutaneous hypersensitivity that we know is present in many humans during migraine attacks. So they're not necessarily capturing the headache, they're capturing the cutaneous hypersensitivity that comes along with the headache. So the pearl here is that many studies have shown that this kind of hypersensitivity develops after migraine relevant stimuli. And I'll talk about some of those stimuli as we go through. And that this behavioral endpoint is sensitive to many different kinds of migraine therapeutics. So this has been well characterized. The pitfall here is that allodynia is not headache, and mechanisms that mediate allodynia and headache might be distinct. And the critique would be, at the end of the day, we might be developing therapeutic approaches for allodynia, but not for headache. The next behavioral endpoint is exploratory activity. And here you would have a chambered device. You can put an animal inside of that chamber. You might have cameras at the top of the chamber, or there might be photo beams that you can use to measure movement of the animal, either horizontally or vertically. The animal's standing up on its hind limbs here. If you looked from the top, you could measure where the animal moves over time. You could track that. You can plot it as a bar graph. And the concept with this particular model is that physical activity is negatively influenced by headache. And the pearl is that that's actually part of the diagnostic criteria for migraine, is that the headaches are worsened by physical activity, or people will avoid physical activity because of the headache. So you can actually capture one of the features of the migraine diagnosis here. The pitfall is that it's challenging to really know why the activity changes. Is it because of headache? We think it is, but we don't know that for sure. The other concern is that this assay might be influenced by anxiety, particularly if you're looking at the movement in the middle of an open field. Animals that are anxious tend to avoid the middle, And so care has to be taken in this kind of a model to make sure that you're not measuring anxiety, and what you're measuring is a pain response, or a response that's influenced by the pain of a headache. Here is a 2-chambered device that would be designed to measure light avoidance. And so you could have a rodent in a dark side of the box or a light side of the box. There would be a door between the two. The animal can freely move in whichever side that it wants. You might have video cameras that are recording where the animal is, how long it spends in this chamber versus how long it spends in this chamber. And the concept here is that light sensitivity is common during migraine attacks. So the pearl, again, is that we can capture part of the migraine diagnostic criteria by looking at light sensitivity in these animals. The idea being if the animal stays in the dark side for more than it would normally, then it's avoiding light. If you give it a headache, a theoretically headache-producing stimulus, and it spends more time in the dark side of the chamber, it would be avoiding light, and that might be consistent with headache. The pitfall here is that rodents are instinctively afraid of light. And so this becomes a bit of a tricky measure, because if the animals are avoiding light because they're anxious about light, and at the end of the day, rodents are prey, and so they are anxious about being seen by predators, these animals might be avoiding light because they're anxious about the light. So again, you might need to do parallel anxiety testing to determine whether or not the animals are avoiding light for anxiety about being seen, or whether they're avoiding light because the light hurts. The next endpoint is referred to as facial grimace. And this is images directly taken from the website, the NC3R website, where details about the grimace models can be found. And essentially what you're doing is looking at the facial expression of the animal. And you can look at 5 different features: orbital tightening or tightening of the eyes, and you score this 0, 1, or 2, a nose bulge, a cheek bulge, ear positions, and a change in the whiskers. And the concept is that pain can be detected, headache included, in the facial expression of the animal. So we may be actually measuring headache here and not a reflexive endpoint or something that comes along with headache. So it potentially reflects non-evoked pain is the pearl. The pitfall is that there's potential for investigator bias here, but that, of course, is true for anything I'm talking about today. But here, it's a very subjective measurement that one is putting on the facial expressions of these animals, and that certainly has the potential for bias. So blinding really needs to be incorporated correctly here. The other thing is that the scoring is really only 0, 1, or 2, and so that statistically doesn't allow for a lot of power when one is trying to look for what might be subtle changes across a dose response or a stimulus intensity. The next type of behavioral paradigm probably requires a little bit more explanation than the previous ones. This is condition place preference or avoidance. And I'll start with avoidance first. And so the setup here is that you would have a multi-chambered box, and there would be a door between the chambers, but the door would be closed on a training day. And you might give an animal a hypothetically headache-producing stimulus and confine it to one side. You might come back later that day or the next day and give it a control, a vehicle stimulus that would not likely produce headache, and you confine it to the other side. Now, the sides of these chambers, the floor would be different. It would have a different texture. It might be any number of ways it would be different. The colors on the walls, the patterns on the walls could be different. You could have one scent or odor on this side and a different scent or odor on the other side. And the idea is to get the animal to remember the context where something happened. And so it might take a few training sessions over days, but what you can ideally do is cause the animal to avoid this chamber where it was conditioned with a headache-producing stimulus. So that on the actual testing day, you could come in, you can open the doors, you could put the rodent in whatever side that you wanted and let it freely move wherever it wants to go. And you're recording all of this with video cameras. And the animal should avoid the context where it got a headache, if it remembers that context. So that's condition place avoidance. Essentially, the condition place preference is just the opposite of that. What you would do is create a headache or a headache-like state in the animal, And you might pair that animal with a headache relieving drug or treatment on one side, and you would pair it with a placebo or a vehicle on the other side. So it would get headache relief in this chamber, but not this chamber. You condition the animal across days. You come back on the testing day, and now you don't give it any drug at all. You open up the doors, you let the animal go where it remembers getting headache relief, and it will spend more time in the chamber where it received relief from its headache. So the concept here is that animals avoid contexts where pain is present, where they experience pain, and they prefer context where pain relief occurs, assuming they had pain in the first place to actually be relieved. The pearl here is that both of these techniques might be capturing headache and not, again, a surrogate for headache, something that comes along with headache. They may actually be measuring the headache itself. The pitfall is that this is very labor intensive. It's most sensitive to stimuli, whether they cause headache or relieve headache, that act very quickly. Ideally, the headache would start within the context of this chamber, or it would be relieved within the context of the chamber. That's how these experiments work best. And this type of experiment is influenced by the production of reward. This is a classically used experimental paradigm in the field of drug abuse. You can pair animals with drugs of abuse, and they will go back to those contexts on testing days when they have no drug because they remember the rewarding effect. So you have to make sure that your stimuli or your drugs are not producing a reward on their own. So next we'll transition into the kinds of stimuli that would cause a headache-like response in a rodent, and here are a list of what I'm going to cover now. The first here is stimulation of the dura. And so in rats, you would implant a cannula through the skull here that allows you to inject a stimulus right onto the outer layer of the meninges, the dura. And that stimulus might be an inflammatory soup, a cocktail of inflammatory mediators. It might be a single cytokine like IL-6. It could be CGRP. It could be almost anything. And then subsequent to the injection, you would test hypersensitivity of the periorbital region of the hind paw, as we described earlier. You might test exploratory activity in a chamber like this. You might test light avoidance. And the concept is that headache is most likely or most often due to nociceptive input from the meninges. And this is something that has been known for many years and is the most likely cause of the actual headache phase of a migraine. And so the pearl is that there is confidence that headache actually occurs here because you are directly activating nociceptors that innervate the meninges by injecting a noxious stimulus directly onto the meninges. So your confidence in the fact that a headache is present is fairly high. The pitfall is that, at least in rats, this requires a craniotomy to put the cannula into the skull, and that's an invasive condition. And the stimuli that we actually inject onto the meninges, while we think they may have relevance for headache, it's not clear whether those stimuli are actually present within the meninges in humans during headaches. And so there's questions associated with that. The next is just a slight modification of what we just covered, and this is applying this to mouse. And you just see the skull here. What the advantage in a mouse is that the mouse skull is relatively thin, and so at the intersection between the skull plates, you can inject through the skull without the need for a cannula, so it's much less invasive. And we don't worry about the craniotomy influencing the behavioral responses. And then you can train mice to sit in what might be a paper cup like this and test their periorbital hypersensitivity. So the concept, again, is the same as what we just talked about. The pearl here is, again, that we know that headache occurs because we're directly stimulating the meninges. But here we don't need a craniotomy, so that's an advantage. And we can also use genetic tools that exist in mice. Pitfall being that the injections and the behavioral testing in mice are actually quite technically challenging. Next is nitroglycerin injection. You can do this either once or you can do it across days. You can inject nitroglycerin or a vehicle. You can do behavioral testing across those days. On any given test day, you would habituate the animals. You might test them before you give the nitroglycerin injection. You wait some time, you test them after the nitroglycerin injection. You put them back, you come back a few days later, and you test them again. The concept here is that nitroglycerin triggers attacks in about 75% of people with migraine. And so The pearl is that you're using a translational model, a stimulus that we know can cause a response in both a rodent and a human. So one could go back and forth. The pitfall is that the doses of nitroglycerin in rodents are often high, and there are sometimes concerns about the vehicles that are used to dissolve the nitroglycerin. Next is cortical spreading depression, which we think is associated with aura, the aura phase of migraine. This is something that can be induced in the cortex and recorded in the cortex, and you can measure these characteristic shifts in voltage that happen during CSD. You can measure this on single neurons, you can measure it in brains, you can measure it in slices of brains. People have gotten very sophisticated in recent years, and you can now have animals in chambers that are hooked up to wires directly to computers, and you can measure CSDs while the animals are moving around. Concept here is that CSD is linked to aura and possibly also to headache. The pearl is that this is a very distinct and relevant mechanism within the brain that can be timed and it can be induced and measured under controlled conditions. The pitfall is that the connection between CSD and migraine without aura is unclear, and the methods that are used to study CSD are often invasive. Next, we transition into models where there are multiple stimuli. And so this would be a situation where you would give an animal an initial stimulus. Maybe it's IL-6 on the dura, maybe it's CGRP, maybe it's in the bottom here, it's stress, repeated exposure to stress. And that would cause an initial behavioral response in the animal that would resolve after you stop the stimulation. Then the animal enters what's referred to as a phase of latent sensitization, where it looks otherwise normal. But then you can come back to the animal and give it a stimulus that in a normal animal would not cause a response, but in an animal that was previously exposed to whatever the stimulus is, it causes a response in those animals. The second stimulus can be a mild pH stimulus on the meninges, an donor, any number of things. The concept here is that most migraine attacks are episodic, and one attack may influence subsequent attacks. The pearl with these models is that they have an ictal phase, two ictal phases actually, and an interictal phase. And so one could study the interictal phase, you could study responses after either of the ictal phases, plasticity that develops between the phases. And so it's really able to capture aspects that may not be captured in the other contexts, the other types of models. Pitfalls here, similar questions exist as with the endpoints that were tested in other models. You're really using the same kind of stimuli, you're really using the same kind of behavioral endpoints. And so many of those concerns that I talked about earlier would translate over to these types of models. Next is another multi-stimulus context here, except in this case, the first stimulus would be repeated exposure to some kind of medication, whether it's a triptan, an opiate, acetaminophen, a cannabinoid, that would cause a response when the stimulus is repeatedly administered. The responses go away, you enter the latent sensitization phase after the exposure to the medication stops, and then again, you can come back to the animal with a normally non-noxious or subthreshold stimulus and precipitate a response only in the animals that were previously treated with the drugs. Concept here is that we know that excess medication use can worsen headache disorders and cause medication overuse headache. The pearl here is that we can use the exact same drugs that are used in humans, the same triptans, the same opioids. The pitfall here is that the medications in these models are typically given to naive animals that don't actually have headaches. And so those mechanisms might actually be different than the mechanisms of the headache itself. Finally, another multi-stimulus model here. In this case, the first stimulus would be a traumatic brain injury, some kind of head injury. There's a response to the head injury, the animals recover, there's a latent sensitization phase, but now they're sensitized or primed to a follow-up stimulus that they wouldn't normally respond to. That could be bright light, that could be a nitric oxide donor. So the concept here is that TBI can lead to post-traumatic headache. The pearl is, this is an opportunity to study a very poorly understood headache subtype. You can study the early post-injury mechanisms, you can study the sensitization phase, or you can study how stimuli become problematic later in the model. The pitfall here is that there's various ways to induce TBIs in rodents, and it's unclear which of those is most relevant to human head injuries. There are still many questions that exist around this. So just to summarize, we talked about a variety of endpoints many of which have translational relevance that have been taken backwards from humans into animals. We've talked about a number of different stimuli. In all cases, they are designed to replicate something that we think is happening in humans. The concept would be that each of these endpoint or stimuli is actually mimicking something relevant in the context of human headache. The pearls here, many features present in human headache can be tested in animals. Animal models can be used to study mechanisms and responses to stimuli that we just can't test in humans because of concerns or inability to do the kinds of experiments that we might want to do. And the pitfalls here, again, no animal model can fully recreate the experience of headache or migraine. And the models may, in many cases, not be actually capturing head pain. They might be capturing something that comes along with head pain. They might involve injuries, and questions exist over translatability of dosing. Thank you for your attention.